Okay, so in this video, we will introduce and prove the so-called integral test. So here's the statement. We consider the series of the sequence an, so a1 plus a2 plus a3 and so forth, the infinite sum, where an is equal to fn. So there is a function of n that equals an for every positive integer n. And here are the two assumptions. We assume that f of x, our function, that equals the terms of our sequence for the positive integers, is eventually non-negative and decreasing. Now, eventually means that we don't care about the behavior of f of x early on, as long as at some point on the function is non-negative and decreasing. So this could happen when x equals 5 up to infinity, or f could be non-negative and decreasing starting when x equals 100 up to infinity. The reason why we say eventually is we know that when we look at the convergence of a series, we can always ignore the first few terms, as a finite sum of real numbers is a finite number, and this does not affect convergence. So even though early on the function may not be non-negative or may not be decreasing, it's okay. We simply have to ignore the first few terms of our series up to the point where f becomes non-negative and becomes decreasing. And this will simplify our life quite a bit, as we will not have to worry about the behavior of f of x when x is small, but only look at when x is large enough. Will our function be non-negative and decreasing? And when the answer is yes, then we can apply the integral test. And here's the conclusion. Then our series converges if and only if the improper integral of f of x from 1 to infinity converges. So this is very simple. What we'll do is we'll trade the question of convergence about this series for the question of convergence of the improper integral. As in this case, by now we have developed so many techniques of integration that we have a bit more tools for integral problems than for series. And if the improper integral converges, automatically the infinite series converges. If the improper integral diverges, automatically the infinite series diverges. So whatever happens to the improper integral, the same conclusion will apply to the infinite series. And when we prove the result, we will in the end be left with this simpler formulation. So in simpler terms, and you will see this very easily from the proof of the result, that the infinite series is roughly the size of the improper integral. And what I mean here roughly, I mean in terms of order of magnitude. So either both will be finite or both will blow up and be infinite. And that's really the intuition. And when you look at the argument and the proof, you will see why this is really intuitive. And this is an argument that we've used a few times previously. So let's prove the result. And we'll assume that right from the beginning, starting at 1, the function is non-negative and decreasing. As again, if it were not the case, we simply have to move up further enough along the x-axis to reach the point where f becomes non-negative and decreasing. To simplify the argument, we'll assume that this begins at 1. One last comment before we start the proof. We could have the series beginning at 5, and then the integral would also begin at 5. If the series would begin at 1,000, the integral would also begin at 1,000. So the lower bound of summation and of integration is irrelevant. We'll assume here that it is 1, but it does not matter. So we assume now that beginning at 1 the function is non-negative and decreasing, so it may look something like this, where n here is a very large integer. So let's construct rectangles above each interval of unit length. As each interval has length 1, the area of the rectangle is again the width times the height, but as the width is 1, the area will simply be the height of the rectangle. And of course this is the graph of the function y equals f of x. And we'll use in this argument the left-hand point to provide us with the height of our rectangle. And now we ask, well, what is the area of each rectangle? The key point is, as we've just said, as the width is 1 for each rectangle, the area is simply the height. So here this is f of 1, f of 2, f of 3, up to f of n. But our assumption was that f of n is equal to an for every n. So the area here is f of 1, which is simply equal to a1. The area here is f of 2, which is simply equal to a2. The area here is f of 3, which is equal to a3. Up to our nth rectangle, the height is fn, so the area is fn, which is simply equal to a sub n. So now if we add up the first uppercase n terms of our series, a1 plus a2 plus a3 up to plus an, we have the total area of these rectangles. This is, of course, can be written concisely using sigma notation. We are summing a sub lowercase n, the terms of our sequence when n begins at 1, all the way up to positive n. And then we can make a comparison with the total area of these rectangles with the exact area below f of x. From 1 to n plus 1, clearly, the total area of the rectangles will be larger than the exact area below f of x. This is, of course, the integral, as x goes from 1 to n plus 1. So we now have our first inequality. We now have that the finite sum of the first uppercase n terms of our series is at least this definite integral. We need another inequality in the opposite direction. We have to show that the sum is also less than something almost of this type. Let's look now at a second picture. So we'll reproduce this almost exactly, but with a slight twist. Again, assume this is the same picture. It's still the graph of y equals f of x. Doesn't really matter. And now the key point is, for each interval, we pick the value of the function at the left-hand point to give us the height of the rectangle. We will now do the opposite. We'll pick the y value of the function at the right-hand point to give us the height of the rectangle. So we'll start here with this rectangle. And now let's look at the area of each rectangle. Again, the width of each rectangle is 1, so the area is the width times the height. As the width is 1, the area is just the height. The height here is f of 2, but f of 2, by assumption, is equal to a2. The height here is f of 3, so the area is f of 3, which is equal to a3, again by assumption. And here the height is f of n, and so the area is f of n, which is of course equal to a subscript uppercase n. So, if we add up a2 plus a3 plus a4 up to an, we get the total area of these rectangles. So this is the sum of an, and now be careful here, n begins at 2. N's at uppercase n, so this sum is the total area of these rectangles, which we can now compare to the exact area below f of x. And we can clearly see that the total area of these rectangles will be, at most, as we're missing a little bit of area for each rectangle, the exact area below the curve f of x, beginning at 1 up to n. The only annoying part here is that we are missing a1. Well, this is quite simple. We can add a1 on both sides, and this will still preserve the inequality. So let's do so. So if this is at most this, we can add the same amount on both sides. This will preserve the inequality. So let's add a1. Well, if we add a1, we can squeeze it in the sum by starting not at 2, but at 1. So we're going to add a1 to the sum. And here we'll simply need to add a 1 because we can't combine it to the integral. So we'll have the integral from 1 to n, f of x dx, plus a1. And now we have our two key inequalities, which we will now combine into one statement. So we have the same partial sum here, the sum of the first uppercase n terms of our infinite series, this is no bigger than the integral of f from 1 to n plus a1, and this is at least as big as the integral of f from 1 to n plus 1. And now, all that remains, as this sequence of inequalities is valid for every positive integer n. So if this is true for all n, we can now let n approach infinity. Let's see what happens. Now, two comments. We can do so because everything here is positive, right? We are assuming that we are summing non-negative terms, and we are integrating a function that is assumed to be non-negative. So everything we have here is non-negative. So in the limit, as n goes to infinity, the inequalities will be preserved. So if we do so, what happens? Well, n plus 1 will go to infinity, so this will become the integral from 1 to infinity of f of x dx, is at most the sum from 1 to n, but as n goes to infinity, the partial sum becomes the infinite series. Is at most, letting n go to infinity will give us the integral of f from 1 to infinity. Plus, of course, a1, as a1 is a constant. And now we're essentially done. Look at these two inequalities and think of the improper integral. What does it represent? As f is assumed to be non-negative, the integral of f of x from 1 to infinity represents the exact area below this curve, from 1 to infinity. And if you think about it, there are only two possibilities. Either the area is finite, or the area is infinite. Those are the only two options. Let's suppose first that the area is infinite. Then this integral would be infinite, and then the infinite series is at least as big as infinity. Well, there's not many options there. The infinite series must also be infinite, therefore they both diverge. And so if the improper integral is infinite, so is the series, as it is at least as big as the improper integral, and so they both have to diverge. Let's now assume that we are in the other possibility, where the improper integral converges, therefore is finite. So if the area below f from 1 to infinity is finite, look at the series now. It's between a finite number and a finite number plus a real number. So this is now bounded between two real numbers. But think about this. You're adding a1, then a1 plus a2, then a1 plus a2 plus a3, then a1 plus a2 plus a3 plus a4, and so forth. And as at some point the terms are non-negative, the sequence of partial sums is now increasing. As you're adding more and more positive terms, the sum gets bigger and bigger and bigger. So what you have here is an increasing sequence, but if the improper integral is finite, this increasing sequence is bounded. And now we can quote simply the monotone convergence theorem. If you have an increasing sequence that is bounded by some fixed real number, automatically the sequence must converge, which proves that when the integral is finite, the series is finite as well, therefore it converges. And we're done. When the integral blows up, the series blows up, so they both diverge. When the integral is finite, the series is finite, and as it is increasing, it must converge by the monotone convergence theorem. And you can see by the two inequalities that ultimately we were correct. As if, beginning at 1, the function is non-negative and decreasing, we have just shown that the difference between the series and the improper integral is at most a1. And you can picture this easily on the real line. Suppose you have here the real line. This is the improper integral. Suppose it does converge, then it has some real value. Here you have the improper integral plus a1. So the length of the interval here is exactly a1, this minus this, and the infinite series lies between these two values. Well, as the total distance of the interval is a1, this series can't be further away from the improper integral than by a1. a1 is just a real number, and you see that again, the infinite series will be very close to the improper integral. So if you remember the geometric argument and the proof, then this should not be very hard to remember. When you think of summing the numbers as giving you the total area of the rectangles, and when f is positive or non-negative, this represents the area below f from 1 to infinity, then you think of both as area of almost the same region, then the series is approximately the size of the improper integral. So again, to conclude, you should simply remember this. So whenever the improper integral blows up, the series blows up. Whenever the improper integral converges, the series converges as well. As if this is finite, this is also finite. And that's it.